Hello everyone, we are presenting our robot learning final project, which is imitation learning for generalizable household manipulation. As robots move into home and caregiving roles, general purpose manipulation becomes essential. Behavior cloning enables learning from demonstrations but struggles with compounding errors, especially in varied real-world settings. Our projects test how well behavior cloning, Dagger, and transformer-based behavior cloning models handle complex tasks like peg insertion, aiming to advance robust and deployable household robotics.
We used the many-skill simulation and dataset. Here's our formulation, containing the states including the robot arm position and velocities, and two camera images, one from the robot GRISP, which is the hand RGBD, and one that has the global view, which is the base RGBD, and the action is in 8 dimension. The hypothesis that we're testing is how much better a transformer performs compared to an MLP in imitation learning, where the policy maps from states to actions.
Here's a demo of the expert action. Our baseline model is a simple behavior cloning setup, with parameters originally chosen for the easier push cube task. We kept those settings, and with 2000 updates, batch size of 32, RGBD input plus joint info, we retrained the model directly on the harder peg insertion task to test generalization. The RGBD image is compressed by a lightweight CNN, fused with a 25D robot state, and passed through an MLP to produce 8 joint actions. Here's the loss curve. As you can see, the validation loss ranges between 0.1 to 0.2, which is pretty high. And here is a rendering demo. This tiny network performs well on PushCube, but in peg insertion it fails. The arm hovers, drifts, and never lines up with the hole. For our behavior cloning model, we expanded the state encoder and added a second camera. The robot now sees through 2 RGBD wrist cameras, one on the hand for detail and one at the base for context. Each image passes through its own ResNet 18, modified to handle depth, and we combine the outputs into a visual feature vector. The robot state, which includes joint angles, speeds, and tool pulls, flows through a deeper MLP to produce a compact embedding. We merge this with the vision features, then feed the result into another MLP to predict 8 continuous joint actions. As you can see from the loss curve, this loss is way lower than the baseline behavior cloning implementation. The rendering shows that now the robot arm can recognize where the block is, but cannot lift it up and cannot identify the target hole.
We also tried to mitigate the distribution shift in behavior cloning through Dagger. Due to the lack of teleoperation equipment, we developed a modified Dagger approach. Instead of querying an expert, we performed a nearest neighbor action search based on the cosine similarity between current observed state and states in the metadata set. To improve over our original multimodal MLP-based policy, we designed a more expressive transformer-based behavior cloning model that leverages attention over robot positional state and observational RGBD visual inputs of both hand camera and the base camera. We passed each RGBD image into a vision transformer where we modified it to accept 4 channel of input RGBD. In parallel, we passed the robot positional state into a transformer encoder pipeline. It has a linear embedding layer, a learnable positional encoding MLP, and 2 layers of transformer encoder. Finally, we fused all the inputs through a concatenation and 4-layer MLP head to produce an action. And here's our transformer curve. As you can see, the transformer behavior cloning method results in the lowest validation loss compared to both the MLP-based behavior cloning and the baseline. This matched to our hypothesis. We think this is because transformer can capture the long-range dependencies due to its self-attention, and can also capture the complex correlations from its cross-attention mechanism between the multimodal inputs. From this rendering, we can see that the transformer-based behavior cloning can pick up the peg and aim to the hole. The key takeaways: 1. Transformers outperform MLPs in behavior cloning when handling rich multimodal input. 2nd, architecture choice can significantly impact performance. We showed this through our MLP-based BC improved from the baseline. So even without the transformer, there is still a significant improvement.